Einstein might be wrong. All hell broke loose in the physics community. Einstein was wrong. Let that sink in for a moment. One of the most brilliant minds in human history, the man who revolutionized physics with his theories of relativity, is now at the center of a groundbreaking controversy. A new study, published in recent months, has sent shockwaves through the scientific community, challenging the very foundation of modern physics and calling into question some of the most cherished principles of the universe. If Einstein was wrong, what does that mean for our understanding of reality, and where do we go from here? To truly understand the implications of this study, we need to start with Einstein's legacy, specifically his theory of general relativity, published in 1915. General relativity fundamentally changed the way we understand gravity, space, and time. It replaced Newton's classical view of gravity as a force with the revolutionary concept of gravity as the curvature of spacetime. Einstein's equations elegantly described how massive objects like stars and planets warp the fabric of spacetime, creating what we experience as gravitational attraction. This theory has been confirmed time and again, from the bending of starlight during solar eclipses to the detection of gravitational waves in recent years. But as robust as general relativity has proven to be, it has always had its limitations. For one, it cannot reconcile with quantum mechanics, the theory that governs the behavior of particles at the smallest scales. While general relativity excels at describing the large-scale structure of the universe, galaxies, black holes, and the expansion of space itself, quantum mechanics operates in an entirely different realm where uncertainty, probability, and wave-particle duality reign supreme. For decades, physicists have struggled to bridge this divide, searching for a unified theory of quantum gravity that could describe both the very large and the very small. Now, it seems the cracks in Einstein's theory are becoming too large to ignore. The new study in question, conducted by an international team of astrophysicists and published in a leading scientific journal, suggests that the universe is not behaving the way general relativity predicts. Using data from advanced telescopes and satellites, researchers have observed anomalies in the way galaxies rotate, the distribution of dark matter, and the expansion of the universe. These observations defy the predictions of Einstein's equations, pointing to the possibility that our current understanding of gravity is incomplete or even fundamentally flawed. One of the most striking findings of the study involves the mysterious phenomenon of dark energy. First discovered in the late 1990s, dark energy is the name given to the unknown force driving the accelerated expansion of the universe. According to general relativity, gravity should eventually slow this expansion down, but instead, observations of distant supernovae and the cosmic microwave background have shown that the universe's expansion is speeding up. To explain this, physicists introduced the concept of dark energy, which is thought to make up about 68% of the total energy content of the universe. But here's the catch. No one knows what dark energy actually is. It doesn't interact with matter or light, and it cannot be directly observed. Its effects are only inferred from its influence on the cosmos. Einstein's theory can accommodate dark energy through the addition of a cosmological constant, a term he originally introduced and later dismissed as a way to describe a static universe. But the new study suggests that this explanation is insufficient. The behavior of dark energy, as revealed by the latest observations, doesn't match the predictions of the cosmological constant. Instead, it points to a more complex and dynamic phenomenon, one that may require a new theory of gravity to fully understand. And then, there's dark matter. Like dark energy, dark matter is an invisible and enigmatic substance that makes up about 27% of the universe. It's thought to provide the gravitational glue that holds galaxies together, preventing them from flying apart as they rotate. Without dark matter, the observed motion of stars and gas in galaxies would make no sense. Yet despite decades of searching, scientists have yet to directly detect a single particle of dark matter. The new study adds to the mystery by showing that the distribution of dark matter in certain regions of the universe doesn't align with the predictions of general relativity. This suggests that either our understanding of dark matter is incomplete or that gravity itself behaves differently on cosmic scales. But perhaps the most controversial aspect of the study involves the Hubble constant, a key measure of the universe's rate of expansion. For years, scientists have struggled with a cosmic tension between two different methods of measuring the Hubble constant. Observations of the early universe, such as the cosmic microwave background, yield a different value than observations of the nearby universe, such as supernovae and Cepheid variable stars. This discrepancy, which has grown more pronounced with increasingly precise measurements, suggests that something fundamental is missing from our cosmological models. The new study proposes that this tension cannot be resolved within the framework of general relativity. Instead, it points to the need for a new theory of gravity, one that accounts for the effects of dark energy, dark matter, and the evolution of the universe in a way that Einstein's equations cannot. This is not to say that general relativity is entirely wrong. Like Newton's laws before it, Einstein's theory has proven remarkably accurate in many contexts, but just as Newtonian mechanics was eventually superseded by relativity, so too may relativity be superseded by a more comprehensive theory. What might this new theory look like? Several possibilities are already being explored. One is the idea of modified gravity, which posits that the laws of gravity change under certain conditions or at certain scales. Another is the concept of emergent gravity, which suggests that gravity is not a fundamental force, but rather a byproduct of deeper quantum interactions. Still others involve extra dimensions, alternate forms of energy, or entirely new particles. Each of these ideas represents a radical departure from the established paradigm, but all are motivated by the same goal: to reconcile the inconsistencies in our understanding of the universe. The implications of these developments are profound. If Einstein's theory is incomplete, then our entire picture of the cosmos must be re-examined. The age of the universe, the fate of galaxies, the nature of black holes, the origin of time itself, all of these questions are now up for debate. And while this uncertainty may be unsettling, it is also a testament to the power of science. The willingness to challenge established ideas, to admit what we don't know, and to push the boundaries of human understanding is what drives progress. But this journey is far from over. The new study is just the beginning of what promises to be a long and continuous debate. Observational data will need to be verified, alternative theories will need to be developed, and experiments will need to be conducted to test these ideas. The process may take decades or even centuries, but it is a necessary step in our quest to understand the universe. As we look to the future, one thing is certain: the legacy of Einstein will endure. Even if his theory of general relativity is ultimately replaced, his contributions to science will remain a cornerstone of human knowledge. His work paved the way for countless discoveries and inspired generations of scientists to think boldly and creatively about the nature of reality. And in that sense, Einstein's spirit will continue to guide us, even as we venture into the unknown. So was Einstein wrong? The answer is both yes and no. His theory of general relativity was a monumental achievement, a testament to the power of human ingenuity. But like all scientific theories, it is not the final word. Science is a process of continual refinement, and the discovery of new evidence is not a failure but a triumph. It shows that we are still learning, still questioning, still searching for the truth. And in that search, we honor the very essence of Einstein's legacy. This new study doesn't just raise questions about Einstein's theory of general relativity, it forces us to rethink the most basic assumptions we've made about the universe. At the heart of these assumptions lies a concept we often take for granted: time itself. Einstein's equations fundamentally link space and time into a single fabric called spacetime. But what if time, as we understand it, isn't real? What if it's merely an illusion, a construct created by the human brain to make sense of an incomprehensible cosmos? Some physicists have already started exploring this unsettling idea. In a universe where Einstein's equations don't hold true, the nature of time might be radically different. The new study suggests that dark energy, the force accelerating the expansion of the universe, could actually be a manifestation of something more fundamental, something that ties space, matter, and time together in ways we haven't yet understood. This line of thinking opens up a Pandora's box of philosophical and scientific questions. For instance, is time flowing in one direction as we experience it, or is it just as static and eternal as the space we occupy? In Einstein's universe, time is relative. It speeds up or slows down depending on how fast you're moving or how close you are to a massive object. But this new research hints that time might not exist as a continuous flow at all. Instead, it could be an emergent property arising from deeper physical laws we haven't yet uncovered. If time is an illusion, then so is causality, the very idea that one event leads to another in a linear sequence. This challenges not only physics, but the entire framework of human understanding. How do we make sense of a universe where events don't unfold in the way we perceive them? How do we reconcile our lived experience of the past, present, and future with a reality that may not conform to those divisions? These questions are not just theoretical. They have profound implications for technology, consciousness, and the future of humanity. Take quantum mechanics, for example. At its core, quantum mechanics defies our classical understanding of time and causality. In the quantum realm, particles can exist in multiple states simultaneously, and if events can influence one another regardless of the distance between them, a phenomenon known as quantum entanglement, this has led some physicists to propose that time itself might be a byproduct of quantum processes, an emergent feature of the universe that arises only when observed. If true, this could mean that our perception of time is not a fundamental property of reality, but a quirk of human consciousness. Now imagine the technological ramifications of this realization. If time is not a fixed linear dimension, but something that can be manipulated or even bypassed, then the possibilities for human innovation are staggering. Quantum computers, already on the cutting edge of technology, could take on an entirely new role by harnessing the quantum nature of time. These devices might one day allow us to peer into the past or predict the future with unprecedented accuracy. They could revolutionize fields ranging from medicine to artificial intelligence, unlocking capabilities we can't yet imagine, but this also raises ethical concerns. If we gain the ability to manipulate time, what does that mean for free will, for morality, for the nature of human existence? These are not questions we can afford to ignore. As history has shown, every scientific breakthrough brings with it a host of unintended consequences. The more we learn about the universe, the more responsibility we bear in deciding how to use that knowledge. Another profound implication of this new study is its impact on the search for a unified theory of everything. For decades, physicists have sought to reconcile general relativity with quantum mechanics, a task that has proven notoriously difficult. String theory, loop quantum gravity, and other proposed frameworks have all attempted to bridge the gap, but none have achieved universal acceptance. This latest research suggests that the problem may lie not in our theories, but in the assumptions underpinning them. If Einstein's equations are incomplete, then the entire foundation of modern physics may need to be re-examined. One promising avenue of research involves the concept of holography. According to the holographic principle, the entire universe might be a projection of information encoded on a distant lower-dimensional surface. This idea, first proposed in the context of black hole physics, has gained traction as a potential unifying framework for gravity and quantum mechanics. If true, it could mean that the three-dimensional reality we perceive is just a shadow of a deeper, more fundamental reality, one where the rules of general relativity no longer apply. The implications of holography extend far beyond physics. If the universe is a hologram, then reality itself may be an illusion. This raises profound questions about the nature of consciousness and the role of humanity in the cosmos. Are we merely observers of a preordained cosmic drama, or do we play an active role in shaping reality? Some physicists and philosophers believe that consciousness might be the missing piece of the puzzle, a fundamental aspect of the universe that is as important as matter, energy, and spacetime. If so, then understanding the true nature of the cosmos may require us to look inward as well as outward. This brings us to one of the most intriguing aspects of the new study, its implications for the multiverse. If Einstein's equations are incomplete, then our universe may not be the only one. Instead, it could be part of a vast, interconnected multiverse where different regions of spacetime operate under different physical laws. This idea, once relegated to the realm of science fiction, is now gaining serious scientific traction. The discovery of dark energy and the anomalies in the Hubble constant suggest that our universe is not a closed system, but part of a larger, dynamic framework. The multiverse hypothesis raises as many questions as it answers. How did these universes come into being? Do they interact with one another? And what does it mean for our understanding of existence? If there are infinite universes, each with its own unique properties, then the very notion of truth becomes relative. What is real in one universe may be impossible in another. This challenges not only physics but philosophy, forcing us to confront the limits of human knowledge. As we grapple with these questions, it's worth remembering that science has always been a process of exploration and discovery. Every time we think we've reached the limits of understanding, new evidence emerges to challenge our assumptions. Einstein himself understood this better than anyone. He famously said, "The important thing is not to stop questioning. Curiosity has its own reason for existing." Those words are as true today as they were a century ago. The new study that challenges Einstein's theory of general relativity is not the end of the story. It's the beginning of a new chapter in the history of science. It reminds us that the universe is far more complex and mysterious than we can imagine, and that our journey of discovery is far from over. As we continue to push the boundaries of knowledge, we must remain open to new ideas, willing to question even our most cherished beliefs, and ready to embrace the unknown. What lies ahead is uncertain, but one thing is clear: the universe still has many secrets to reveal, and as we stand on the brink of a new era in physics and cosmology, we can take comfort in the fact that the spirit of inquiry that drove Einstein and his contemporaries continues to inspire us today. The road may be long and fraught with challenges, but it is a road worth traveling, a journey into the heart of the cosmos, and into the very nature of reality itself. As the new research forces us to re-examine Einstein's general relativity, the questions it raises about the multiverse go beyond mere academic curiosity. If our universe is but one among an infinite number, each with its own distinct properties and physical laws, then how does our place in this multiverse shape our understanding of existence? This is not just a question of physics, it's a question of meaning. For many physicists, the multiverse hypothesis is both thrilling and unsettling. It suggests that everything we know, the galaxies, stars, and planets, may be part of a larger framework that operates under principles we have yet to comprehend. If each universe is governed by its own set of laws, then the constants we take for granted, such as the speed of light or the gravitational constant, may vary from one universe to another. In some universes, stars might not form at all. In others, life as we know it might be impossible. This raises the profound question: why does our universe exist in such a way that it allows for life to flourish? This question lies at the heart of what scientists call the fine-tuning problem. The laws of physics in our universe appear to be exquisitely calibrated to support life. If the strength of gravity were slightly weaker, stars might never form, and the universe would remain a cold, dark void. If the electromagnetic force were slightly stronger, atoms might not hold together, and matter as we know it could not exist. These precise conditions have led some to speculate that our universe might be part of a multiverse ensemble, where countless other universes exist, each with different properties. In this framework, the existence of a universe like ours is not a miraculous coincidence, but an inevitability, one of countless configurations in an endless cosmic sea. But even this explanation raises deeper questions. If the multiverse exists, then how did it come to be? Is there a mechanism that generates these universes? And if so, what is its nature? Some theories suggest that the multiverse arises from quantum fluctuations in a higher dimensional space. Others propose that it is the result of eternal inflation, a process where the fabric of space-time continuously expands, spawning new universes in its wake. These ideas are tantalizing, but they also challenge the limits of empirical science. After all, how can we observe or test the existence of other universes when they are, by definition, beyond our observable horizon? The inability to directly observe the multiverse has led some critics to dismiss it as speculative metaphysics rather than science.